Welcome everyone. Welcome to the session 8, accelerating machine learning. Today we have 4 great talks. Our first speaker is the Juqi Lin. He's the second year PhD student in University of Science and Technology of China. His research interest is the AI system, such as GNN training and distributed deep learning training. Juqi, please go for it.
Thank you, Jing. Can you hear me?
Yep, I can hear you. You can start.
Okay. Hello, everyone. I will briefly introduce our work, ParGraph, scaling GNN training on large graphs via computation over caching. This work focuses on hi, Jing. Could you help go to the next page?
Yep. Oh, sorry. Yep.
Yeah. Okay. This work focuses on accelerating GNN sampling training. Before the introduction of ParGraph, I will firstly introduce the existing training workflow as well as the challenges and the motivations we observed. The top left figure shows the GNN sampling training workflow. The workflow consists of 3 phases: sampling, data loading, and computation. And for each iteration, first, a mini batch will be sampled from Graph Store server, and then, as shown in the red-colored part, the required features for this mini batch will be collected and sent into GPU memory. We call this part together with step 2 and step 3 as the data loading phase. At last, the mini batch and its data will be fed into GNN model for computation. Okay, and we evaluated this training workflow and found that the data loading has high cost throughout the whole training cycle. We can see from the top right figure. Okay, Jing, could you help slightly put up the the second page?
Yeah.
No, the previous one.
Previous slide. I mean the first page.
Yeah. Okay. That's much better. Thank you. And we can see from the top right figure, the data loading phase can cost up to 74% of time during the training. And to understand the problem better, as shown in bottom left figure, we found a huge data volume will be loaded into GPU in each epoch. And the reason to cost this is the redundancy data assessing pattern across different mini batches. The middle column shows the loaded vertex feature number in each epoch, which is nearly 4 times larger than the total vertex number in the whole dataset. So with all of these observations, we propose a cache mechanism to cache frequently visited vertex data in GPU memory. And to better serve cache in multi-GPU training scenario, we propose a GNN-aware graph partition algorithm to achieve better scalability. Hi, Jing, could you help go to the next page?
Yep, sure.
Oh yeah, thank you. And this comes to our design of ParGraph. The left side figure shows the system overview of ParGraph. There is a graph store server serving the whole graph dataset and multiple trainers working on different GPUs to train the GNN model. We developed a GNN-aware graph partition algorithm, and in this way, the graph will be firstly partitioned into. Hello? Can you hear me?
Hello.
Hello, can you hear me?
I can hear both of you.
Okay, so I will continue. The graph will be firstly partitioned into different subgraphs, and each trainer works on a dedicated subgraph. There is a loader inside each trainer, and the loader will cache frequently visited vertex data inside the GPU memory. Sorry, it seems I can't see my slides. Okay, Can you hear me?
Yeah, we can hear you. Go ahead.
Okay. And so there is a loader inside each trainer, and the loader will catch frequently visited vertex data in GPU memory. The data loading in paragraph will simultaneously fetch data from graph store server and loader. The results are shown in the right side. The right top figure shows the single GPU training performance. We can achieve up to 3.7 times speed up over DGL. The right bottom figure shows the scalability achieved by paragraph and DGL. And benefit from linear increasement of computation capacity as well as total cache memory. A paragraph can achieve even superlinear speedup in some certain cases. For example, here we can achieve nearly 5 times speedup on the 4 GPU training scenario on ENWiki dataset. Yeah, that's all. Thank you. Any questions?
Hello?
Hello, I may be not.
Yeah, so while waiting for the question from the Chen Chen or the Hoover, let me ask one question. As you know, the many neural networks actually their structure change over the time, evolve over the time. So how your work could handle those neural networks that might change or evolve over the time?
Yeah, that's actually a very good question. So actually, GNN graph neural network in this area, it is new and things can be changed in very short time. Actually, we summarize that there is also this is somehow general framework that use the feature. Since the feature loading is very general in most of GNN training systems, and we observe from this this way and use the sampling and target on sampling training. I think this is some kind of general way to solve the high cost of data loading problem.
Thank you for the clarification. And any questions? And you can ask the question in Zoom chat or over. Okay. While waiting for the question from Zoom chat, let me ask another question.
Okay.
And I'm wondering. Oh, okay. And we got the one question right now. So compared to CNN, why GNN is so special?
Yeah, actually, we observed very special behavior in GNN sampling training, which is totally different from traditional deep learning training, such as CNN. So just as I said, we found that there are lots of data accessing, redundant data accessing patterns in GNN, and this is totally different from traditional CNN. For example, like a computation, like a CNN task, data set may consist of lots of images, and during one epoch training, the image will be only loaded once into GPU memory. However, in GN sampling training, we saw that a vertex may be loaded multiple times into GPU memory. So this helps us provides an opportunity for us to leverage cache to cache the frequently visited data, and thus we can accelerate the whole training performance.
Oh, thank you for your answer. And we got another question by Simon. If we have an MV link between the GPUs, could each worker also use the cache from other GPUs as the first level cache, and then the main memory as the second level cache? Could it be beneficial?
Yeah, I think it is a very interesting point, and my answer is yes. And actually, with NVLink, the communication between GPUs can be very fast, and so we can leverage different. We can put different graph data into different GPUs, and with the NVLink, we can have a higher bandwidth to transfer data, and so this speed can be much faster than communicating between CPU and GPU. So I think this is a very beneficial solution.
Oh, thank you for your answer. I want to ask, I want to add a few more things. So these days, the high-end GPU machine has the MV switch as well as the MV link, and that MV switch actually provided the really high bandwidth, the bandwidth for the communication between all the GPUs in the one machine. Yep, thank you. So we are still waiting for the question. You can ask any question in the Zoom chat. While waiting for another question, let me ask one more question. So I'm also wondering if we could use any compression or the deduplication technology to reduce the overhead of data transferring between GPU and CPU for your application, your approach. What is the and if we try to use the compression or deduplication technology, what do you think that would block the usage of this technology in your work?
Yeah, actually, this I think is a very interesting point. The redundancy in our work actually, there are two redundancy patterns in GN sampling training. So we can say there is an inter-batch redundant vertices and intra-batch redundant vertices. So compression or deduplication can only be applied on a batch on one mini batch and reduce intra-batch redundancy. And however, we observe that there are no more than 7% of redundant vertices in one mini batch. So this may indicate that there are only little room for this optimization. But I think that this is good to try.
Oh, yep. Thank you. Thank you for your answer, and thank you for your great talk today. And let's move on to the next talk.
Okay, thank you.
Thank you. Thank you, Chichi. Our next speaker is Bamya Chen. Bamya Chen is a fifth-year PhD. Oh, okay. Let me move on to the next slide. Bamya Chen is the fifth-year PhD candidate in the Department of Computer Science of the University of Illinois at Urbana-Champaign. He's working in the Distributed Protocol Research Group. His research interest is to improve the system performance of distributed machine learning frameworks and privacy of the federated learning. Bamya?
Yeah,
Please
can you hear me?
go for it. Yep, I can hear you.
Yeah, okay. Thanks for the introduction. Hello, everyone. My name is Bamya Chen. I'm going to briefly talk about our batch system for fast and effective placement of machine learning graphs. As machine learning models are getting bigger, ML models cannot fit on single GPU memory. To address this issue, a ML graph is split into multiple subgraphs, and those subgraphs are placed on the multiple GPUs. The question here is how to split and place those subgraphs on GPUs. In other words, the device placement on machine learning graphs. The current state-of-the-art approaches use reinforcement learning techniques. They show decent performance of the training step execution time. However, they require very long placement time ranging from 2 hours and even 3 days. They also require retraining when a target ML model or deployment configuration changes. In this paper, we present Betchy, a fast ML placement system that uses an algorithmic approach. We propose 3 competing placement algorithms for memory-constrained environment. We adapt our parallel job scheduling algorithms to propose 2 memory-constrained algorithms called ETF and MSCT. We also present a strawman based on the topological order called mtopo. We prove that the placement generated by the MSCT is within a constant factor of the optimal under certain conditions. More details are in the paper. We apply this placement algorithm to a popular ML framework, TensorFlow, but we encounter several challenges to achieve fast and effective placement. We propose optimization techniques to address these challenges. To deal with TensorFlow collocation requirement, we use co-adjust placement that considers the collocation constraint while scheduling. To minimize too much communication overhead, we use co-placement mechanism that places certain operators on the same device. To deal with the massive number of operators, we propose operator fusion and also propose scale-up heuristic for avoiding cycle generation in the fusion process. Lastly, we provide sequential communication support to tackle the different network architectures assumed by the algorithms and in the real environment. Our evaluation results show that Betchy achieves about 700 to 206,000 times faster placement time than the learning-based approaches. Betchy also places well by showing only up to 6.2% higher step time than the expert placement. I will show our evaluation result in details in the next slide. Could you move to the next slide? Yeah. The top table shows placement times for an image classification model, Inception V3, and a language model, NMT, with the 2 learning-based approaches, and our Betchy system. For Inception V3, Betchy finishes the placement within only 10 seconds, which is about 700 to 43,000 times faster than the learning-based method. For NMT, Betchy shows about 3,000 to 206,000 times speed up. The bottom table shows the average step times of the ML models placed by our Betchy system. mtopo's placement shows up to 34% higher step times than the expert placement, and METF's placement shows minus 4.5% to 6.2% speed up, and MSAT shows minus 6.2% to 1.9% speed up. This concludes my talk, and thanks for your attention. I'm happy to answer any questions.
Hello?
Hello?
Oh, sorry. Yeah, I was muted. Yeah. Yeah, we got one question from Huba. Do you run all algorithms and choose among them the best placement?
That's a good question. The short answer is we don't, but we could easily do that. So our system runs the placement algorithm specified on user. So a user can run all the algorithm and pick the best of them. Also, it is possible in our case that run them all in parallel and pick the best one because our algorithms are very fast.
Okay, thank you for your answer. And okay, we have another one from the Chen Chen. What is the major replacement time source in current state of art method?
The placement time, I think the major placement time cause. Is that the question?
I think what does the time source means? What's the I mean the type? What's okay? The replacement time.
Yeah, I think the question is meant to point out the placement time for the current state of the art method. Yeah. So since they need to train the reinforcement learning model, so just training those the model takes very long time, since the reinforcement learning method is based on the trial and error. So they need to have multiple trials to find the best placement. So that is the main source for long placement time in the current state of the art method.
Okay, thank you. Thank you for your answer. And we are waiting for, while we are waiting for the question from Chen Chen, let me ask one question. So that your project, the batches, the approach actually relies on the static profiling. For example, you calculate the queuing delay statically on the schedule. But I think it might not always work. For example, there are several unpredictable dynamic factors in the system that might does not work in your approach. For example, such as the temporary network congestion or the slow the temporal and the power throttling or the machine failure. So in this case, do you have any idea how to extend the queuing model to handle these dynamic behavior of the system in real-world application?
I see. I think the question is how to use our placement algorithm in the dynamic environment where there's a network congestion, and which also change the communication overhead and the computation overhead due to the interference and so on. Is that right?
Yeah, that's correct.
Yeah, I think that's an interesting question. So I think in that scenario, we can easily apply our placement algorithm for that by running our algorithm periodically. Since our algorithm is so fast, and also generating the profile, those kind of the profile is also very fast. So we need to sample only like 5 or 6 samples in running. So if we have those kind of profiling result, we can run our algorithm after that and to adapt those dynamic environment adaptively.
Thank you. Thank you for your answer. Okay, and we are still waiting for question in the Zoom chat. Please, if you have any question, please ask your question in the Zoom chat. And while waiting for question, let me ask another question. So, so in your approach, I specifically use the M-topo and METF and SCP. May I ask why you selected these 3 specific algorithms?
Oh, that's also a very great question. So we picked the M-topo because that is the strawman, and also when we first encountered this kind of problem, then that is the kind of intuitive, easy solution. That's why we use that topological based placement as a sort of another baseline. And also we chose SAT and ETF because of the 2 major reasons. First, they are the best performing algorithm for the parallel scheduling. Since MSAT was proved to be close to the optimal, as I mentioned in the paper and also in the paper in the slide, and also their assumed model is very close to the ML graph, which is the DAG graph. So those 2 reasons are why we picked the SAT and ETF as a target algorithm for the placement.
Oh, thank you for answering. Thank you for answering to my questions. And
My pleasure.
please, if you have any question, please ask your question in chat. We are waiting for your question. And while waiting for questions, let me ask one more question. Okay, so what happens when the co-locating operators on the same device to minimize the data transfer is not possible because the memory issue?
Oh, actually, that is also a very great question. So we thought about that issue. So this actually we encountered that issue when we reduce the memory limit for each GPU. So that is also in our paper and in the evaluation. So in that case, it's like our first attempt is just to disable those co-location to avoid generating too big chunk of the operator is placed on the same on the GPU. But I think as we can see in the evaluation that those co-placement is very beneficial to minimize communication overhead. So I think one way to trade off those benefits from the operation, the co-placement and the high memory uses of the co-placement is we can, for example, like we can set some kind of threshold for each group of the co-placement. So let's say up to like up to 1 GB of the operator can be placed on the some device and something like that. So if that is the case, then we can have some kind of trade-off between those two aspects.
No. Thank you. Thank you for your answer. Okay, I think it's time to move on to the next talk. Thank you, Bomyer.
Thank you. Thank you for thank you for all, and thanks for that.
Okay, let's move on to the next talk. Our next speaker is Dr. Chen Chen. He got a PhD in computer science and engineering from Hong Kong University of Science and Technology. His research interests include distributed deep learning systems and big data analytics systems and networking. Dr. Chen Chen, please keep going.
Okay, thank you for the introduction. Hello everyone, I'm very glad to present the lightning points of our research work, semi-dynamic load balancing, efficient distributed learning in non-dedicated environments. Machine learning has been very popular in the recent years, and it has become increasingly common to train models in non-dedicated environments with heterogeneous hardware or dynamic resources. In non-dedicated environments, because workers may have inconsistent resources in quantity or quality, there would be stragglers that may largely slow down the model convergence. However, resolving stragglers for distributed model training is non-trivial because of the distinct properties of model training workloads. For example, typical model training process is composed of thousands of short iterations in seconds or even sub-seconds. Those iterations share the same computation graph. And meanwhile, all the samples in a batch is usually processed as a whole in a tensor-based batch processing style for faster processing in modern machine learning frameworks like TensorFlow or PyTorch. Therefore, the traditional load balancing methods like static load balancing or dynamic load balancing would be ineffective or incompatible for modern machine learning frameworks. And actually, we found that machine learning workloads should be load balanced in a semi-dynamic manner. That is, we keep the load static within each iteration, but dynamic across different iterations. And we adjust the load at the iteration boundaries by tuning the work batch size. Actually, semi-dynamic load balancing is a great fit for model training workloads. First, because different iterations share the same computation graph, The behavior of the recent iterations can play as a valuable reference for the near future. This way, we can measure the worker status at the iteration boundaries. And second, under the back synchronous parallel scheme, we can have a natural time opportunity to centrally collect all the workers' progressing status at the iteration boundaries. So there's almost no other overhead. And third, we can have the hyperparameter worker batch size at the iteration boundaries, and worker batch size can ideally control the load of worker in each iteration because each sample will have the same commutation operations in that batch. Can you move on to the next slide, Jin? Hello, Jin? Oh, thank you. And in this work, we have combined the semi-dynamic load balancing scheme to the current back synchronous parallel correlating scheme and propose LBBSP. The objective of LBBSP is to equalize the batch processing time of all the workers by tuning the batch size prior to each iteration. And this turns into different challenges for CPU and GPU clusters. For CPU clusters, our profiling work shows that for a standalone CPU worker, its batch processing time is linear to the batch size. However, the challenge is that in shared production clusters, the CPU worker performance may vary drastically with the temporal resources, especially when training with leftover resources. And in contrast, in GPU clusters, the good news is that GPU performance is much more stable across consecutive iterations. But the challenge is that for a standalone GPU worker, its batch processing time is non-linear to the batch size and hard to be profiled at runtime because there is a parallel processing scheme in GPU and there is a saturation effect and there is a memory limitation. For the detailed profiling, please refer to the paper. Based on the own characteristics, we propose an analytical method for CPU clusters with a novel prediction approach to get the performance of each worker in the upcoming iteration. And that approach considers both the driving resources of CPU and the memory amount. For GPU clusters, we propose a numerical method that iteratively refines the batch size of each worker towards the ideal batch size scheme. We have implemented LBBSP as a pluggable Python module for modern machine learning frameworks, including TensorFlow and PyTorch. And our test bed experiments on EC2 shows that LBBSP can accelerate model convergence by up to 54%. Okay, that is all for the Nightling introduction. Welcome for any questions.
Hello? Oh, sorry. It's, yeah, so we got the one question in the Hoover. What is the convergence, the early stopping condition in slide 22?
Actually, I've answered it, Hoover. And the convergence in our experiments means reaching a near optimal accuracy target. And we have listed the accuracy target in the paper in section 5.1. You can refer to the paper for the detailed setup. Thank you.
Okay, thank you. We got another question from the Zoom chat by Simon. I don't understand the LBBSP has even smaller per update time compared to ASP inception V3 application. Since ASP is totally non-blocking, thus should have optimal per update time, but was convergence as a trade-off?
Yeah, this is a very good question. I was very curious when I found the phenomena. And actually, ASP should be good, but it is limited by the fixed batch size. I have elaborated the problem in section 5.2. And actually, the reason is that by shifting some samples from a slower worker to faster worker, the utilization of the faster worker can be larger. That means that if we shift 10 samples from worker 1 to worker B, and worker 1 to worker 2, the slowdown of worker 2 is much smaller than the speed up of worker 1. And this means that the utilization of different GPU workers has changed. So the phenomenon mentioned by Simon is that it's under the assumption that the utilization of different GPUs are of the same, but that is not the case. By shifting the samples across different workers, we can increase the GPU utilization, increase the overall GPU utilization. So actually, LBBSP can achieve a better hardware efficiency, especially for the large models like Inception V3. For the detailed elaboration, please refer to section 5.2. Thank you.
Thanks for answer. And we have another question from Chen Chen. Can we also apply semi-dynamic load balancing for model parallelization to parallelize the training? This question is by Hao Wang.
Okay, thank you for the question. Yes, of course. In this work, we focus on data parallel model training, but actually data parallel model training is compatible with model parallel, because in data parallel, there is a set of logic workers, but actually each logical worker can be composed of a series of servers. In that case, we can combine the data parallel with model parallel, and for each logical worker, we can apply LBBSP.
Yep.
That is all for my answer.
Thank you for your answer. And we got another question from Simon. Batch size affected the computation time, but what about the data loading? Data loading time of Cypher 10 is short and it could be ignored, but for ImageNet, data loading is slow and will be affected by the batch size. I think he makes really good point. I mean, based on my personal experience, in some application, data loading also is really overhead.
Well, it depends on the storage of the data, right? For GPU worker, actually the frequency of batch size changing is low. So and actually there is a data cache scheme in modern machine learning frameworks. That means that if the data sample batch size is not changed, then at the same time of the current sample processing, the batch of the next iteration is already prepared in memory. So for GPU workers, that is not a concern. For CPU worker, currently, because the CPU computation is slow, so the communication or the data loading can be shaded under the computation time. So in our test by experiments, the data loading is not a problem.
But in many real-world applications, data size could be really large and does not fit into the aggregated memory size of the whole cluster, even the whole cluster. In that case, the most typical configuration is that we store all the data in the central storage server, and every epoch we read the data from the central distributed storage to the GPU, the training client machines. So the disk buffer or the caching in the main memory does not, is not efficient to handle those kind of large scale training workload.
Okay, sorry, I did not consider this problem because in your experiment, the data are stored locally in each worker. So the data transmission problem is not a concern. And for the network file system, I think I've seen in related papers that there is a data prefetching scheme. So we can prefetch the batch for the upcoming iterations prior to each iteration.
Okay, yeah. Thank you. Okay, we got another question from Simon. Even if I already put the entire ImageNet data set to the shared memory, the data loading could still be slow for GPU workers.
Of course, first, it is not necessary to put the entire image line to the shared memory. And regarding the data loading, I'm not sure because in my experiment, I've not seen the delay from the data loading. Maybe we can discuss this offline. I'm interested in this. Okay.
Okay. So we have 4 more minutes. So I wanna discuss this issue, little more things. And for example, the most ideal case would be like this. And data load for the data loading, we need some CPU resource, and then we also need some GPU computation to execute the CUDA memory copy between to transfer the data from the CPU to GPU. That CUDA copy operation might slow down the GPU operations. So my suggestion is that you can measure the performance gap between the most ideal case that does not suffer any CUDA memory copy operation and what you are doing now. So when you can make some synthetic the program that actually pre-patch some limited subset of the batch in the GPU memory, and then run your iteration using the preloaded the patches, and then you can measure that would be the ideal case without any memory copy overhead, and then that gap between the ideal case and then what it is now would be the performance gap. So you can check on that, and by doing that, you can measure what's the overhead of data loading.
Okay.
Yep.
Thank you. Sorry, I'm not a hardware guy, so I'm not very familiar with the GPU mechanism. I'm just solving this problem from an algorithm perspective. And from my test by environments, I found that the data loading part is not, it does not consume much time, especially when the batch size for for consecutive iterations are of the same. If you change the batch size, then maybe there is a small slowdown, but because in GPU workers, the batch size is not frequently changed because GPU performance is relatively stable. So in general, the data loading part is not a concern for time, at least in my experiments. Thank you.
Okay. It depends on the application. So, okay, yeah. Thank you. And we have one more question. Last question from Chen Chen. Is it the ABBSP application agnostic? And what benchmark did you test it on?
It is application agnostic because we implement LBBSP in a dedicated path module called Batch Size Manager. And that module only connect the worker execution status and adjust the batch size. It can treat the iterative model training process as a black box. It connects which worker is the fastest and which worker is the slowest, and then adjust the batch size allocation scheme. And the benchmark we use are several vision models like Inception V3, ResNet, and Session8. I admit that there is a limitation on those models because we only consider the vision models. And in the future, we should consider the language models, which are much larger. But I think LBBS itself is application agnostic.
Thank you. Thank you for your talk today, Dr. Chen Chen. And it's time to move on to next talk.
Thank you.
Our next speaker is Dr. Rajay Vishwanathan. He's the software engineer in machine learning platform team at Uber Technologies. His research work focuses on improving the machine learning training efficiency and the machine learning developers' productivity. She got a PhD in computer science from the University of Wisconsin-Madison. Dr. Rajay, please go for it.
Thanks, Jen, for the introduction. So today I'm just going to present a really quick overview of our work on accelerating distributed machine learning for multi-tenant settings using a communication framework library called ML Fabric. The problem we are trying to solve is that of training a machine learning model, typically a DL model or an LDA model, which is very large, using data that is spread across multiple nodes. So that is what is distributed machine learning is. There are many frameworks that allow you to do distributed machine learning. For example, you have very popular frameworks in the industry like TensorFlow, PyTorch, Harvard, and there are many other things that came from the academia like Boson and the parameter server. But if I want to classify all the different types of distributed machine learning frameworks, I'll bucket them into two different architectures. One is the parameter server architecture, where your model is basically stored in one or more servers, and a lot of workers are basically reading their local data shard, and they pull the model from the server, update it using their local view of the data, and then push the updates to the server. The second one is the MPI-based systems, where instead of having servers and workers, you basically have end nodes that use MPI-based communication, typically all reduce, to run synchronous HTTP to in a distributed fashion keep updating the weights. This is super popular, with many accelerators being built for MPI-based systems like NVLink, etc. from NVIDIA. Irrespective of what the architecture is, the one thing that we want to note is DML algorithms are both compute and communication intensive. And the reason they're both compute and communication intensive is that the model sizes are growing, right? Like you see in deep learning, people are training models with like billions of parameters. And typically for even computing the updates using like a few batch sizes takes like few hundreds of milliseconds. The other thing to note that is because these model sizes are large, and every node, in case of MPI-based system, has the model and then it has to do the all reduce, the all reduce operation is also heavily compute intensive. Even though you have like 10, 40, 100 gigabytes of, GBPS network links, they still take a significant amount of time, like a few hundreds of milliseconds, to actually, exchange all the gradients and update the model locally. And this is true whether it is a parameter server architecture or an MPI-based system as well. In the MPI-based system, it's the worker bandwidth that gets consumed. In the parameter-based systems, the worker has to talk to the server, and that's what causes the network overhead. The third thing I want to note is stragglers are unavoidable in the shared infra. In the last talk, we saw, hey, compute stragglers, right? One thing we want to note is that it's not just the compute that straggles, it's also the network bandwidth can fluctuate in a shared infrastructure, especially when you don't have a dedicated cluster. The bandwidth that is available between, let's say, the worker and the server, or between two workers, can fluctuate over time. And in our work, we note that both compute and network slowdowns affect time to completion for DML algorithms. Next, we'll see how these impact the different DML algorithms that are there. With respect to DML algorithms, there are two very popular algorithms that we are typically using. One is the asynchronous algorithms, where workers just update the model asynchronously. There's no barrier between the multiple workers. Asynchronous algorithms are typically implemented using the parameter server architecture, in which case when the model size increases, the network load at the server is very high. And once a worker is very slow, we also see that the delay effects start affecting the convergence. What do we mean by delay? The delay is effectively the difference in the model that a worker reads and the model to which its update is applied. And for a slow worker, the delay tends to be high, and we've seen that the slow workers tend to have high delay, and which affects the convergence of the model. And finally, for parameter server architecture, the model replication overhead also exacerbates the issue. For synchronous algorithms, the slowest worker, whether it's slow because of compute or whether it doesn't have enough bandwidth, kind of determines the time per iteration. So higher the time that one worker takes, they kind of hold all the other workers from completion. This is a typical problem with stragglers in synchronous parallel. Next slide, please. We aware of this problem, we propose a communication library which essentially wants to solve improve the performance of DML training by taking a holistic view of both the network and the computing delays. So ML Fabric is a communication library which sits below the DML application layers. So it could sit below a TensorFlow worker or a PyTorch worker. And what it happens is it intercepts all communications. The architecture has a centralized scheduler, which has knowledge of the bandwidth that is available at each node. It has complete knowledge of the delay of the updates, and it schedules the transfer of gradients between the different entities that are participating in the DML algorithm. And it also coordinates aggregation, which is kind of the first time we are doing aggregation in the context of a parameter server, where multiple workers' updates can be aggregated at a third location and then transferred to the server. ML Fabric takes advantages of aggregation, ordering, and also dropping the state updates of the worker to speed convergence. We measure the performance of ML Fabric against the state-of-the-art systems like existing parameter server architectures, ring-reduce algorithms using synchronous STT, etc. And I want to just highlight the key results that we have. More details, please refer to the paper. The first thing is we found that ML Fabric, with ML Fabric, we are able to get DL model to converge using an asynchronous parallel algorithm. And we find that for certain straggler settings, like for certain compute, for actually a variety of compute and network settings, we are able to get up to 3x faster than ring-reduce. The second thing we want to notice, for just a synchronous algorithm, ML Fabric doesn't perform better than ring-reduce in all straggler settings, but for certain straggler settings where one worker is like really slow, ML Fabric is able to drop the update or kind of change the aggregation pattern and thereby has 16% faster time per iteration. We observe that the gains improve to 20% when gradients are allowed to be dropped. The paper has more details. We compare not just DL algorithms, we compare LDA algorithms, we compare against in-switch replication, etc. I will encourage you to go look at it. I would like to end this talk and would like to take more questions.
Thank you for talk. Okay, let me check on the Huba, and there's no question in the Huba. Okay, there we got the question from Chat by Simon. In your video slide, the sign of the regularizer in the update equation seems wrong to me. So was the equation one in the paper? Okay, I think this one is, we need the equation to answer this. You need the equation to answer this question. So let me take this one for the offline discussion. So we are waiting for questions. So you can ask any question in the Zoom chat. While waiting for question, let me ask one question. So as you know, for the large scale distributed training, the more and more the company and people in the industry have adopted the high bandwidth InfiniBand networks like the 100 gigabps LIDIA or the more recently 200 gigabps HDR with the very low latency RDMA. And also those, you know, and the modern GPUs, so high-end GPU servers has the 8H, the InfiniBand HCAs or the 4H, the 100 gigabps HCAs, and also they have MV switches, so that their network bandwidth is really, and networking bandwidth is really higher. And then this is a little bit different from your experiments. You mostly use the 10 gigabps network. So in this, the advanced environment and how well your approach will work and how much performance gain can deliver.
So that's a good question. So are you questioning how effective would ML Fabric be? Let's say the bandwidth is like 200 gigabytes. Is that the correct way to put your question?
Pardon?
Is the correct way to put your question is like how effective will ML Fabric be if the network bandwidth were 200 gigabytes per second?
200 gigabits, and that's actually one HCA, and then modern GPU machines, servers actually have multiple 200 gigabps or 100 gigabps the network interface?
Yeah, so in this work, at least, we don't focus on running machine learning in dedicated networks / dedicated clusters. We focus typically on we focus typically on shared infrastructure. Like, for example, when you have things in AWS, or when you have in a data center where you do not have you do not have RDMA enabled, you do not have network accelerators, in the sense that you so one is the shared infrastructure part of it. The second part I want to highlight is the model sizes are also going really large. Like, it's uncommon. It's very common to use for like billions of parameters. For example, I don't want to quote GPT, but GPT is one of the very popular models out there, which has like 175 billion parameters. And when you have 175 billion parameters, whether you have 100 gigs or 200 gigs, it's still going to the network bottleneck for distributed learning is still going to be significant.
Okay, thank you. And okay, we got another question from the Chen Chen by Ali Tariq. I'm curious about what distributed configuration you used when comparing ML Fabric to base parameter server, and why. By distributed configurations, I mean how many workers and parameter servers?
So we consider 30 workers with across spread nodes with 2 GPU cards in each node. And we for most of our base experiments, we fix like 4 parameter servers. And we also found that, so one common way to avoid the server bottleneck is to actually keep increasing the number of servers that are there, so that the model parameters that each server is responsible for reduces. So the network load at each server will go down. But what we observed is that as you keep sharding your model across many servers, and when you're running asynchronous SGD without a proper synchronization barrier between the rate of updates at each server, for as we increase that, we see that the convergence gets affected. So for our base thing, it is 4, but we also have an experiment that varies the servers and see the impact of increasing the servers on convergence of asynchronous SGD.
Thank you for answer. And we have one last question. Do you have any assumptions on how many jobs are collected in your multi-tenant experiments? For example, how workers are placed in the cluster across jobs? This question is very less true. Yeah.
Yeah, that's a good question. We do not assume, we assume it is kind of random. We don't do, at least in our cluster, we know that our experiments are very controlled, right? So we don't make any strong assumptions that the workers are rack local or device local. We assume it is random, but we abstract out this detail by modeling the bandwidth available to each server. So it could be possible that if two workers are situated in the same rack, they probably have a high bandwidth. And workers that are situated are placed on different racks have low bandwidth between them. But we don't make any strong assumptions. We basically model the available bandwidth between the workers rather than the location themselves.
Okay, thank you for your answer. And actually, Simon left 2 more questions about that equation. So let's continue our discussion in the offline after this session. Thank you. Thank you, Rajay, for your great talk, and thank you everyone for all the presentation in the session 8. And this is that's the end of the session 8.
Thank you very much, Jinkyu. I would like to encourage everyone, including the authors, if you have more questions, to go together. We have a 30-minute break now, and we'll come back at 2:30 New York time for the panel on data center architectures. So see you soon. Thank you.
Thank you.